Introduction to Quantum Mechanics. Before we talk about the details of this chapter, so let's talk about the history of the quantum mechanics first. During the late of the 19th century, okay, so the knowledge of the physics, right, can be categorized into the two. The first one is the classical mechanics from the Sir Isaac Newton, and the second one is the electromagnetism by James Clerk Maxwell. So during that time, physicists believed that every knowledge in the universe, right, can be explained by these two main subjects here. But however, the early of the 20th century, there are the two experiments, the blackbody radiations and the photoelectric effect. So these two experiments cannot be described using these two knowledge here. So it means that we must have the new knowledge that we can use to describe these two experiments. So that's be the beginning of the quantum mechanics. So now in this chapter, we just mainly talk about the electromagnetic wave that can behave as particle. Okay, so we just call it as a photon, and the energy of the photon must be quantized. The quantized just mean not continuous. When we talk about the Max Planck, okay, the Max Planck here. So he is the one that tried to understand and describe the black body radiation. So we're going to talk about this one later. Okay. So he said that the energy of the oscillator is discrete. Okay, so let's just ignore this word oscillator. So the thing is, you need to know that the energy is discrete or quantized. It means that we can describe the energy as the integer number of the h times the f, where the n is to be the 1, 2, 3, and etc. So now this h is just called the Planck constant, having this value. So let's talk about this one later. And now the f is going to be the frequency of the oscillator in the unit of the hertz. Okay, so it means that this energy of oscillator must be an integer number or just multiple of the h times the f. Actually, the idea of this relation, right, you can see from this picture. Okay, so when you have object on the incline, so now you just want to move this object of the incline, right? So you can see that the potential energy of this object, right, will increase continuously. So why I say that? Because, okay, so let's say that the height of this position, right, the height is just equal to the h. So okay, so now you can see that the potential energy, the gravitational potential energy of this object, right, is equal to U, equal to the mg and then times the h. Okay, so this will be the gravitational potential energy of this object. But however, let's consider this this picture. So let's say that we have the object, right, it's just on the step, and we just want to move this object up to the step, something like this. Okay, so let's say that the height of each step equal to let's say equal to a. Okay, equal to a. So now in this case, it means that the potential energy of the object, right, U, must be equal to the n times, okay, the integer numbers of the m, g, and the a, right, n times the m, g, and the a. For example, if initially the object is in here, right? The potential energy equal to 0. But then when we move the object to this step, okay, so now the potential energy equal to the mGa. But then if we move to this step, the potential energy equal to the 2 times the mGa, okay, because this is equal to the A and this equal to the A, so then we have the 2 A's here. So the potential energy here must be equal to the 2 times the mg and the A, okay. So you can see that in this case, right, the potential energy of the body or of the object is going to be an integer value of the mg and then times the A, just the same as this one, okay. So it means that the energy of this object must be quantized or discrete. So then this will be the list of the topics that we just want to cover, okay. So the first, we talk about the experiment. We have the black body radiation and we have the photoelectric effects, and then later we talk about the momentum of the photon, because we say that the photon is going to be the quantization of the particles of the electromagnetic wave. So it means that it must have the momentum as well. And then we just want to talk about an experiment using the results of the momentum of the photon, right? Okay, and then to describe the experiment, it's called the Compton scattering. And then finally we talk about the wave particle duality. So let's say that if electromagnetic wave can behave as a particle, it should be that the particle can behave as a wave as well.